Hi. In the last couple of experiments, we've been playing around with the bipolar junction transistor. In this experiment, the book introduces us to a very different kind of transistor, one that turns light into an electrical current. And in this experiment, we'll ultimately use it to turn light into sound. So for this experiment, we still have the 5-volt regulator that we had for the previous experiment. And if you followed through the previous book, if I tell you that this chip here is a 555 timer chip, you should be able to recognize that this wiring configuration is to operate the chip in an astable mode. And in this mode, it basically operates as an oscillator outputting a square wave, and the timing, the period of that oscillator, is set by this RC circuit here. So at the moment it's not driving anything useful, it's just got a simple resistive load, and I've got the meter set up so that it's measuring the voltage, the AC voltage across that load. So let me fire it up and let's see what we get. So there we're getting 168 millivolts, and we're getting a frequency of around 2055 Hertz. It's dancing around a little bit, but it's around about that figure. So what can we say about that frequency? Well, that frequency is within the audio frequency range, which ranges from 20 Hertz up to around 20 kilohertz. Although only the very young will be lucky enough to hear the frequencies at the upper end of that range. 2000 Hertz or 2 kilohertz is well within that audio range. So if we attach a speaker to this circuit, then we should be able to get an audio output. So let's do that next. So now I've modified the circuit to be driving this speaker from pin 3, which is the output pin. And you can see that is just connected via a capacitor there. That's just to block any DC component, which of course we don't want if we're driving a speaker. So all being well, when I power up the circuit again, we should now hear that approximately 2 kilohertz tone. And there it is. Let's shut that off. It's not very pleasant. So now effectively what we have here is an audio oscillator. It's a very limited audio oscillator because at the moment it's just capable of outputting a single tone. Now again, if you work through the previous book, you'll know that pin 5 is a control pin. And if we apply a voltage to that pin, we can adjust the threshold levels for the 555 timer. Now because that pin is not currently being used, it is just grounded via a little decoupling capacitor. But if we apply a voltage to that pin, then we can change the thresholds that control the periodicity of the oscillator. An obvious approach here would be to apply a potentiometer between the power supply and that pin so that you could have a knob to twiddle to adjust the periodicity. But we're not going to go down that route. We're going to go full-on Jean-Michel Jarre mode today and use something a little different. So here's a further modification to the circuit, which is that the decoupling capacitor that was grounding pin 5 has now been removed and replaced with this thing that looks a little bit like a clear LED, but it is in fact a phototransistor. And this is connecting pin 5 from the positive supply rail. So this is the collector that's in the positive supply rail, and then the emitter that is connected to pin 5, the control pin. Now, one difference between my setup here and the circuit shown in the book is that the book has a 3.3K resistor from pin 5, the control pin, to ground. In my experiments, I found that just limited the range, the response that I was getting from the phototransistor too much, and so I removed it. Basically, this transistor works in a very similar way to the 2N2222 bipolar junction transistor that we used in the previous experiments. The difference is that instead of an electrical current being supplied to the base, the base is affected by the amount of light falling onto the transistor. And we can hear the effect of this if I power up the circuit. So here's our tone, but what I'll do now is I'll adjust the amount of light falling onto the transistor. So effectively we've got ourselves a little sort of theremin type affair going on here, where we can change the tone simply by changing the amount of light on the phototransistor, which of course affects the voltage into the control pin, and that is what's causing that shift in tone. Let's turn that horrible noise off. So why is this happening? What exactly is going on? Well, if you recall our previous experiments with the bipolar junction transistor, as the amount of current flowing into the base increased, that effectively lowered the internal resistance of the transistor. So not only did the current from the emitter to the collector increase, but also the voltage. And exactly the same thing is happening here. As the amount of light falling onto the phototransistor changes, so does the voltage between the emitter and the collector. And that is what causes our changing tone. So in the next experiment, just as we found out the characteristics of the PN2222 bipolar junction transistor, we'll run a similar experiment to find out the characteristics of the phototransistor. See you then.